Dear students, in the last lecture we have discussed Nernst equation for half cell reaction and how to apply on Nernst equation on the half cell reaction. Now in this lecture, I will discuss the Nernst equation, application of Nernst equation on the complete cell reaction. So what is the important point for this? The very important point that your complete cell reaction must not have or should not have electron. Means whenever you have any complete cell reaction, that reaction should not have electron. You have to manipulate half reactions or given reactions to obtain a complete reaction in such a manner that electrons will cancel out. So the very and most important feature is that the complete cell reaction, the complete cell reaction should not have electrons. Right? Suppose that if you are giving any equation, suppose that if you are given any equation, and in that equation if electrons are present, then that is not treated as a complete cell reaction, right? Electrons should not be there. How? See how to manipulate this. Suppose that you have Zn solid gives Zn2 plus 2 electron, and another reaction is given Ag plus electron gives Ag, right? Suppose that this half reaction is given, this half reaction is given. This is equation 1 and this is equation 2. Now this is oxidation, this is reduction. Now if you add equation 1, if you add equation 1 plus equation 2, so what you get? Zn solid plus Ag plus gives Zn2 plus Ag solid plus electron. So for the purpose of Nernst equation or any purpose, if you want to write this is a complete reaction, so this could not be considered as a complete reaction. Not considered as a complete reaction. Not considered as a complete reaction. Why? Because see, electrons are present here. So what you have to do to make it complete? What you have to do? You have to see equation 1 plus 2 into equation 2, right? Means equation 2 multiply with 2. So what is the equation now? Zns plus 2 Ag plus will give you the Zn2 plus 2 Ag solid. Now this is a complete cell reaction. Complete cell reaction. Cell reaction, right? Okay, so you can use directly Nernst equation on this. First, what is the value of n here? The value of n is here 2. And what is the value of Q here? Q is equal to concentration of Zn2 plus by concentration of Ag plus square. Right? This is solid, so solid will not appear in the expression of equilibrium constant. Now this is a complete cell. So what you have to write here? You have to write here E cell, right, is equal to E naught cell minus 0.0591 by 2 log Zn2 plus by Ag plus square. So this is the Nernst equation for complete cell. This is the Nernst equation for complete cell. Right? Nernst equation for complete cell. Complete cell. Right? So by using this equation, you can calculate this E cell. E cell is also called EMF of the cell. EMF of the cell, right? E cell is also called EMF of the cell. Okay, and E naught cell. How to calculate E naught cell? So here E naught cell is equal to, see what you have taken. You have taken this is oxidation. This is oxidation and this is reduction, and you are getting adding these two. So E naught of Zn oblique Zn2 plus whatever you have written in the equation, that value you have to take, plus E naught Ag plus oblique Ag. Don't write here 2 Ag plus gives 2 Ag, because you know multiplication will not affect this E naught value, right? So this is a reduction and this is oxidation. So this is reduction. This is standard reduction and this is standard oxidation. So this is SOP and this is SRP, right? Standard oxidation potential plus standard reduction potential. We can write in one more way this equation. This we can write like this. E naught of Ag plus oblique Ag minus E naught of Zn2 plus by Zn, right? So here this time this is reduction and this is what? Reduction. So this time these two are SRP minus SRP. Means if you wish to take here reduction on both the electrodes, so what you have to do, which one is the anode here and which one is the cathode? See, this is anode because oxidation is taking place here, and this is cathode because the reduction is taking place here. So if you taking reduction on both, because this is standard, So if you are taking reduction on both the electrodes, then you have to do E naught reduction. So you can simplify this E naught reduction of cathode minus E naught reduction of anode. Right? So these are the different ways how to find out E naught cell. Many times students are doing mistake here. See, there are two methods. One, at anode oxidation, at cathode reduction. So what you have to do, take standard oxidation potential, take standard reduction potential of anode and cathode and add. Or if you are taking reduction potential on both, then you have to subtract from cathode to anode. So both will give you the same result, right? For example, this, see, E naught of Zn oblique Zn2 plus, this is 0.76 volt, and E naught of Ag plus oblique Ag, this is 0.80 volt. So if you want to E naught cell, if you want to calculate E naught cell, so E naught cell is equal to, if we take E naught of Zn oblique Zn2 plus E naught of Ag plus oblique Ag, so this is equal to 0.76 plus 0.80. So this is equal to 1.56 volt. And if you want, so you can take E naught Ag plus oblique Ag minus E naught Zn2 plus oblique Zn. So this is 0.80 minus, now this becomes minus, when you change the couple, this will be minus. So minus 0.76, so this is equal to 1.56 volt, right? So whether you are calculating E naught cell by taking oxidation at anode and reduction at cathode and respective E naught values, or reduction on both and subtracting anode from cathode, in both way you will get the same answer, right? Now see this equation, Nernst equation for complete cell, and by using this equation you can evaluate EMF of the cell, because E naught cell is also called EMF of the cell, right? Now see, in this equation, if Q is equal to, in the above equation, in equation B, see this equation B, if Q is equal to K equilibrium, then what will happen? Once Q is equal to K equilibrium, EMF of the cell is 0. Because now cell reactions are under equilibrium. Right? And delta G is also equal to 0. So once, or vice versa you can say, means if cell reactions are under equilibrium, delta G is equal to 0, so EMF is equal to 0, so Q is equal to K equilibrium. Both way you can justify this. So what will happen? Your Nernst equation 0 is equal to E naught cell minus 0.0591 by N log K equilibrium. This is equation, or you can write E naught cell is equal to 0.0591 by N log K equilibrium. This is equation C, and this is also a very important equation. Right? Now see, E naught cell. Now you have two methods to calculate E naught cell for any complete cell or any half cell. Right? Means standard electrode potential of any particular electrode or standard potential of the cell you can calculate in this way also. If equilibrium constant is given, if the magnitude of equilibrium constant is given, then you can very easily calculate. Now at this point you can put KSP, you can put Ka, Kb, whatsoever it is given, and this equation is also applicable for half cell as well as complete cell. Right? So you can write here that this E naught cell is equal to E naught cathode minus E naught anode, or if you have taken reduction on both, E naught oxidation plus E naught reduction. So this is a simple equation, and you know this now your cell reaction is equilibrium, and no further electrical and chemical energy cannot be converted into electrical energy. Now at this stage, in all these situations, whatsoever I have written here, in all this situation, now chemical energy cannot be converted into electrical energy. See, if delta G is equal to 0 is given for any reaction, or EMF is equal to 0 is given for any reaction, or Q is equal to K equilibrium, any one condition, if it is given, because all are equivalent. So now in this situation, in this condition, further chemical energy cannot be converted into electrical. Right? Now what you have to do, either you disturb the equilibrium. Now you disturb the equilibrium by adding some salt or some reversible ion, or by some other means, Until or unless you are not disturbing the equilibrium, your cell will not work further, means chemical energy cannot be converted into electrical energy. And you know, this state is called rundown state of the cell. This state is called rundown state. Rundown state means in common man language you can say cell discharged or battery discharged, right? So for example, if you take the example of your mobile phone, so mobile phone battery discharge means when battery percentage is 0, means your battery is now under equilibrium, means in your battery chemical reaction, what is happening in your inside your battery chemical reaction, for which delta G is equal to 0 or EMF is equal to 0 or Q is equal to K equilibrium. Now again you have to recharge your battery. So when you are recharging means you are disturbing the equilibrium, and again the process will initiate. Okay, now further chemical energy will convert into electrical energy. So when a cell reaches at this stage, further chemical energy cannot be converted into electrical energy, right? So all these things are related to each other. Okay. Okay. So see, this is a complete Nernst equation. This one is the complete Nernst equation, equation B for a complete cell, right? See, dear students, one question given to you. So if nothing is mentioned, then every equation or every representation, you have to always think from this side to this side. Whatever is happening, you can read in the same manner. See here, Zn, start from here. Zn is converting into Zn2 plus, right? And MnO4 H plus Mn2 plus, MnO4 is converting into Mn2 plus. So in the same manner, from left to right, you can assume the things are oxidizing and reducing. So here this is what oxidation. This is oxidation taking place here. Here this is Zn to Zn2 plus. This is oxidation, and here this is Mn to Mn2 plus. This is what? Reduction. This is reduction, right? And now you can write the equation here. Zn solid gives Zn2 plus, and here concentration is given, no problem, don't write 2 electron. So this is oxidation. Oxidation. And here MnO4 minus gives Mn2 plus. So here you can write 4H2O, balance this equation, plus 8H plus 5 electron, right? So this is a reduction. I think now this is balance, so this is a reduction. So see here, if you see 2 electrons are here and 5 electrons are here. So if you directly add these two equations to get the complete cell reaction, then you will get the electrons in the complete cell. So if electrons were present in the complete cell, you cannot apply the Nernst equation, right? So what you have to do? You have to balance this equation. So you should multiply this equation with 5. This is equation 1, and this equation you have to multiply, because you know E naught will not change, multiplied by 2 So this is equation. Now you can add these two equations. So equation 1 plus equation 2. So what you get? 5Zn solid plus 2MnO4 minus plus 16H plus. This will give you 5Zn2 plus 5Zn2 plus 2Mn2 plus 16H2O. 8H2O. Although H2O has no role here, 8H2O, right? Now what is Q for this? So Q is equal to concentration of Mn2 plus square concentration of Zn2 plus to the power 5 divided by MnO4 minus square H plus to the power 16. Now put the value and find the numerical value of Q. See, Mn2 plus 0.001, so 0.001 square, Zn2 plus 0.015, 0.015 to the power 5 whole divided by MnO4 0.12 to the power 2 and H plus 0.01 to the power 60. Right? So find the value of Q from here. And what is E naught cell? So E naught cell is equal to, you can write E naught Zn oblique Zn2 plus what is happening, you can write directly that, plus E naught MnO4 minus oblique Mn2 plus, so this is equal to 0.76 and 1.507 plus 1.507. So this is equal to 7, 6, 2.267, right? 2.267. 267 volt. Okay. Now E cell is equal to 2.267 minus 0.0591 by how many electrons are exchanging here? What is the value of N? N is equal to 10. See, 2 into 5, 10, 2 into 5, 10, right? So 10 moles of electrons were changing. 10 log 10 to the power minus 3 square and 1.5 into 10 power minus 2 to the power 5 whole divided by 12 into 10 power minus 2 and 10 power minus 2 to the power 60, right? And now you can solve this and get the answer. So I am not going to waste your time, so I have to calculate this and then I will write the answer, right? So now you can solve this. Okay, so calculation of this term will be equal to 5.3 into 10 power 18, and once you solve this complete, so the final answer is log this 5.38. So I can directly write but 2.16 volt. Now you can calculate, no problem, right? So this is the answer. So in this way you can calculate each cell for the given. So I have taken a little bit complicated cell in which involves I mean see here balancing, so that we can cancel the electron and complicated calculation. But okay, anyway, it is the way how to calculate the complete cell potential, or you can say EMF of the cell, right? Now let's start the working of a galvanic cell, right? Okay, now say this is a galvanic cell or voltaic cell, and this particular cell what I have shown here, that is a Daniel cell. So see, this is a zinc rod immersed in a zinc sulfate solution. This is copper rod immersed in a copper sulfate solution. This is I mean mechanism shown here that I have already discussed in the half cell. So this is I mean oxidation half cell, and this is reduction half cell, right? And we have connected C externally, and this is internal connection. See in this salt bridge. So let's talk about this salt bridge. Salt bridge. Salt bridge is made up of here agar. Basically agar is a kind of algae, and it is in the form of white powder. It is coming in the laboratory. So we take agar and agar plus KCl or ammonium nitrate, right? KCl or ammonium nitrate. So and make a paste of this, dissolve in water plus water, and make the paste, right? And homogenize whole system, make the paste and fill in the this tube. This is a glass tube, and freeze it with ice, right? So this will becomes agar, and agar becomes porous, and these are electrolyte are dissociated and present in the form of ions. So this is the composition of the salt bridge. What is the role of this salt bridge? Role of salt bridge: it makes both the half cell makes the electrically neutral, right? So maintain the electrical neutrality electrical neutrality. Neutrality is in both the half cells. In both the half cells. Half cells, right? See how. Another question arises here, how. So all of you are knowing that this solution is positively charged. This is positively charged and this is negatively charged. So what will happen from the salt bridge? This, if we are using KCl, if we have taken KCl, then chloride ions will come this side and potassium ions will come this side. Potassium ion. So these potassium ion, they will neutralize this negative ion, and this chloride ion will neutralize this positive ion, right? So how? So I mean opposite ion. So you can write via the movement of opposite ion to the opposite ion of what? With respect to the solution, charge of solution. Charge of solution. Opposite ion in the different half cells. Different half cell, right? Any special purpose of this use of this KCl or ammonium nitrate here? So this I mean, you cannot use any salt. So you can use that salt of which cation and anion have almost same ionic mobility. So why KCl? Why KCl or ammonium nitrate? Why KCl or ammonium nitrate? So the answer is the ionic mobility means in per unit time the distance traveled by anion or cation under the same potential difference. So ionic mobility of cation is almost equal to the anion, right? So since ionic mobility of this K plus aqueous is almost equal to the Cl minus aqueous ionic mobility. And NH4 plus aqueous and NO3 minus aqueous. So this is the reason why we are using the selective ions in the salt bridge, right? So see role of salt bridge. Now you have composition of salt bridge, role of salt bridge, and why we are using a particular salts in the salt bridge. Now see this is a simple representation of this Daniell cell, and electron are moving from this anode to cathode. This is the negative terminal of the cell. This is the negative terminal of the cell, and this is the positive terminal of the cell. How this negative and positive are determined? This rod is negatively charged with respect to the solution, and this rod is positively charged with respect to the solution. And you know this this is anode and this is cathode, right? So how to write a complete cell reaction? So now I am giving you, a general idea how to write a complete cell reaction. Now I am not considering this is anode, although this is anode, but I am writing this LHS. So now onwards, every time I used to write LHS and RHS. Whatever cell is given, I always do this and always design reduction as a standard. So Zn2 plus 2 electrons gives Zn. Although oxidation is there, I am knowing that oxidation is taking place. I am considering also, but this is the method of writing the half cell reaction and complete cell reaction for a given cell. And I always used to explain in this way only, right? I do not mix and match. You can mix and match, but I will give you the logic why I am taking this, right? So what I am taking here, LHS and reduction. I am taking reduction. And RHS. I am not assuming that this is cathode, this is anode. Although this is anode, this is cathode, but I am not assuming that. And at the end, after a few minutes, you will get what is anode and what is cathode with the logic. RHS also I am writing what reduction equation. Reduction. Now, how to get the complete cell reaction? The complete cell reaction you will get RHS minus LHS, right? RHS minus LHS. So what you get? This minus this. So this will go to the right and this will come to the left. So you will get zinc solid plus copper 2 plus will give you Zn2 plus copper solid. So you are getting the same thing, but the method of writing is standard. This is standard basically. So what you have to do, write the reduction equation for LHS cell, write the reduction equation for RHS, subtract LHS from RHS, get the complete cell reaction without electrons. See, electrons were cancelled out. What is the value of N here? 2. What is the value of Q here? Q is equal to concentration of Zn2 plus by concentration of Cu2 plus, right? This is equation 1. Now what is the EMF of this cell? EMF is equal to, next equation apply, E naught cell minus 0.0591 by 2 log Zn2 plus by copper 2 plus. So this is equation 2. Right? So see, E naught when Zn2 plus concentration is equal to 1 molar and concentration of copper 2 plus is equal to also 1 molar. So in this situation, this whole term becomes 0. So EMF is equal to E naught cell and this is equal to E naught of RHS minus E naught of LHS. So this is equal to E naught of Cu2 plus oblique Cu minus E naught of Zn2 plus oblique Zn. So this is equal to 0.34 minus 0.76. So this is what? 1.10 volt. So this is the standard EMF of this cell or EMF of this cell when the concentration is 1 molar, right? Okay. Now see, I am writing some observation. What observation? When cell is under working, when cell is under working, first point, see what is happening, zinc ions are coming to the solution, so concentration of zinc ion with time will increase, right? Concentration of Zn2 plus ion increases with time in LHS or anode. How to decide that the LHS is anode or and RHS is cathode? Once the EMF is positive, see, once the EMF is positive, see here, EMF you are getting positive. So if EMF is positive, then LHS is anode and RHS is cathode. If your EMF is negative, then what you have to do is switch. Then left hand side is cathode and right hand side is anode. So this is the way to find out anode and cathode. You cannot assume yourself, okay, this is anode and this is cathode. So when EMF is greater than 0, then LHS anode and RHS cathode. And when EMF is less than 0, then the cell reactions are non-spontaneous. In this situation, the LHS is what? Cathode. And RHS is anode. RHS is anode. So this is the way to determine whether which one is the anode and which one is the cathode. So this is the first observation. Now concentration of Zn2 plus ion increases with time in the left hand side, electrode or anode, and see here copper 2 plus is going to deposit on the copper rod. So the concentration, second observation, the concentration of copper 2 plus decreases with time in RHS or cathode. So now see from equation 2, what you can write here, from equation 2, if Zn2 plus increasing, copper 2 plus decreasing, so this Q value is increasing. Q value is increasing means I mean this value is positive. This value is positive or negative? Greater than 1. This is increasing. This is what? Decreasing. So this log Q increasing means what you can say, that this term, this whole term will increase when the cell is under working. So EMF of the cell will what? decrease. EMF of the cell will decrease. So when cell is under working, you can say EMF decreases with time. Right? EMF of the cell will decrease with time. And finally it becomes zero when this becomes maximum value of this. What you can get maximum value of this? One, cell is under equilibrium. When the cell reaction is under equilibrium. So you whenever this ratio is set in such a manner that this attain the equilibrium state, EMF of the cell becomes zero, right? So these are the important variations. So if you plot a graph of EMF versus log Q, so what you get? EMF and log Q. So you will get and this is E naught cell. Right? As the log Q increases, EMF will decrease. Right? And the maximum value is this. Okay? Clear? Good. Okay. So this is the observation with this cell. So hopefully all of you are clear. And now representation of the cell. Representation of the cell. So in the same manner as it is shown here from left to right. So LHS, that's why it is LHS, so left hand side. So zinc is the LHS and this is RHS. So you have to write like this: zinc solid Zn2 plus aqueous reversible ion, some C molar concentration, and two vertical lines represents the salt bridge. This is salt bridge. Salt bridge. And here copper 2 plus aqueous C dash copper solid, right? So this is LHS and this is right RHS. This is anode and this is cathode. So you should and this is bridge. So you can remember this ABC: anode, bridge, cathode, right? So in this way you can represent the cell. And all of you are knowing this vertical line represents the interface. So solid is in contact with this liquid, and this liquid is in contact with one part of the salt bridge, and other part of the salt bridge is in contact with the other liquid, and that liquid is in contact with the rod. So this is the representation of this cell. Okay. So this is the simple representation of a Daniell cell and its working. and underworking what is what is happening and what changes are taking place inside the cell. I have clearly explained, right? So this 1.1 volt is the standard voltage of this cell. See, in laboratory we used to use this type of cell, and see, students are using this type of cell frequently, and you can make it very simple. See, representation. This is also a, you can assume this is a Daniel cell. See, this is a zinc rod and zinc sulfate solution. This is a salt bridge, and this is a copper rod and copper sulfate solution, and this is the connection here. This is the cathode and this is the anode, and you get the what voltage here. So this is the very simple representation. Take two beakers, in one copper zinc sulfate, other is copper sulfate, copper strip, copper strip, zinc strip, and connecting wires, and this is the salt bridge. See, there are many types of cell constructed that in a single beaker you can prepare. In a single beaker, how in a single beaker we can prepare? See, suppose that we have taken such a large beaker, right? And what we have to do, so these two are the porous wall, right? Here you can take zinc rod, here you can take copper rod. This is negative terminal, this is positive terminal, right? And here you can take KCl solution, K plus Cl minus, right? And here you can take copper sulfate, Cu2 plus, SO4 minus minus, and here you can take zinc sulfate, Zn2 plus, SO4 minus minus. Now see, this is what solution is positively charged, so Cl ions were moving this side, they are moving this side, and potassium ions are moving this side. And you can make a cell. This is also the simple representation of Daniel cell, means another representation. Instead of using this salt bridge, we can take a porous wall through which pores of which are permeable for potassium and chloride ions, and you can use this. So these are the different representations of cells. Different representations of Daniel cell. This is one way, this is another way, and this is another way, right? So these two are the same, but different. See, this is I have taken from here, so this copyright, that's why I have written this. See, dear students, measurement of EMF. For this purpose, I have taken a very simple figure here, and let's Understand this. What is this? See, this S is a external source of energy, means S is a cell, external cell, and EMF of this S is more than, it is more than the EMF of X or W, right? So this is, means this is unknown. Reference, you can say, this is known, and this X and W, this EMF to be determined. So EMF of X and W to be determined, right? See other arrangements. What is this A and B? So A to B, this whole arrangement is, you can say, high resistance wire. High resistance wire, right? Now what is G here? G is the galvanometer, and in which we can measure the current, and this X or W, this is the test cell or test battery, you can say, of which potential to be determined. Okay, what you have to do, see, this is movable wire. You can touch this point in this AB at any point. So at point C, point C, if G reads 0, reads value 0, right? Then you can say that the potential of this external battery is equal to the potential of EMF of this X, means there is no current flowing in this circuit. So at point C, if G reads 0, means you can say the EMF of S is exactly equal to the EMF of X or W, means no current is flowing, right, in the external circuit. So this is the simple way to measure the EMF of any cell, right? And you know, if at any point of time this if the EMF of this is less than this, then current will flow from S to here in AB R. And if this is more than this, then current will flow in this arm due to this, not due to this. And once this is equal, so both are balanced. And you know, this is the criteria for reversible and irreversible cells. So whatever I am discussing here, this is an example of reversible cell, right? And one more thing, electrons are moving from here to here. So current is moving from cathode to anode. So current movement is from cathode to anode. current is moving from this place, right? So see, this is the simple representation and measurement of this, EMF of any cell. See, I have taken one figure from your NCRT book, and everybody should write carefully all three figures, and this is very important, and definitely you will get the question in your exam from this. So be careful, and everybody should thoroughly go through this figure. I have taken it from your NCRT book. See, this is very, very important representation, and see here. See, in the first case, E external, see, this is E external, this is the rehosted. You can set the potential as I have explained here, the simple manner. So the same arrangement is here. This is copper, this is zinc, and E external is less than 1.1 volt. What we have taken here, Daniel cell. This is the Daniel cell, 1.1 volt I have calculated. So if E external, see here, if E external is less than 1.1 volt, so what will happening? So electron will drift from anode and move from anode to cathode, and current will flow from here and here. And in this situation, more and more zinc ions will come to the solution. Zn2 plus ions more and more come to the solution, and copper 2 plus ions will deposit on the rod. So this A is a representation of what? Daniel cell or voltaic cell. So this A is voltaic cell. Now come to here in the B. E external is exactly equal to this 1.1 volt. So there is no current, no electron is moving in the external circuit, no flow of current, no chemical reaction, means there is no conversion of chemical energy into electrical energy. Now come to the C part. E external is more than 1.1 volt. This is very, very important point. So this C part, now see, this cell becomes electrolytic cell. Electrolytic cell. So someone may ask, can we convert a voltaic cell into electrolytic cell? The answer is yes. What is the method? This is the method. You can connect this Daniel cell or your voltaic cell with the external battery, and the potential or the EMF of the battery E external is more than the potential of your Daniel cell or your voltaic cell. Then your cell acts as an electrolytic cell. Now what will happen? Now see very carefully. See, zinc now becomes positive. Now this is cathode. And see here in voltaic cell, this is anode, and here nothing to mention anode and nothing is happening here. So now see the polarity of the cell is changed. Now electron is moving from here to here, and in this situation zinc will deposit, because you will get the numerical question on this also. Zinc 2 plus will deposit and copper 2 plus will come to the solution. This is the difference. Right? See the difference. So now it becomes electrolytic cell, and this time zinc rod, Zn2 plus will deposit and copper 2 plus will dissolve. See here, if when E external is greater than 1.1 volt, electron flow from copper to zinc. This time copper, this electron will flow from copper to zinc, means from anode to cathode, and current will flow from cathode to anode. And zinc is deposited at the zinc electrode. Now electrolysis is started. So now this cell becomes electrolytic cell. Right? This cell is electrolytic cell, right? So this figure is so important and you have to note down each and everything. A, here in figure A it is voltaic cell, but in figure C it becomes electrolytic cell and polarity also changes. So at least you should write A and C, right? So dear students, this is the complete working and representation of a complete cell, right? And this is very, very important.